we'd solved our sort of graduation problem with finding the energy associated with the wave, and we worked out the leaky capacitor. Now, we want to do some more with electromagnetic waves. That's what's really the interesting part about this. And the goal is to get to geometric optics, so we can understand how lenses, telescopes, all this sort of stuff works. Now, a first step in doing that is to consider what happens when an electromagnetic wave hits an interface between two different materials. Now, the problem we want to consider then is this. Here you have an interface between two materials having mu1, epsilon 1, mu2, epsilon 2. And we have a wave coming in, making some sort of an angle, call it theta 0. Now, by coming in, I mean that is the direction of the vector k. Remember, the waves have the form, we could use them in the form e to the I k dot r minus omega t, where we took the real part of that. K was the direction of propagation of this plane wave. So this is k coming in like that. Now, when it hits this interface, one of two things has to happen. Either it gets reflected at some angle, let's call it theta 1, or it gets transmitted at some angle, call it theta 2. And now, what we want to do is we want to figure out what will happen at that interface. Specifically, we'd like to know the angles, theta 1 and theta 2, and the fraction of the incident energy that gets transmitted and the fraction that gets reflected. If we've got those, we've solved everything there is to do with that interface. And once we've done that, we'll be able to consider mirrors and lenses and work out all geometric optics, because each of those things will involve something striking an interface, and then the ray either going through it or bouncing off it. Okay, now we're going to need a new parameter that we haven't discussed yet, and that is something called the index of refraction. Usually denoted by n, which is defined to be the ratio of the speed of light in vacuum over the speed of light in the material. In other words, it's a number that basically tells us how much light slows down when it enters the material. Now, we've already discovered that V was 1 over the square root of mu times epsilon. So that means that C, which is 1 over the square root of mu 0 epsilon 0, then C over V is mu epsilon over mu 0 epsilon 0 to the 1/2. Okay, now, given that, we're going to figure out what's going to happen when those rays strike. Now, we know that the electric and magnetic fields are perpendicular to the direction of propagation. Remember, everything went as this triad. So let's take the electric field to be this way. Now, if the electric field there is that way, call this E0. That's the incident. Now, we know that E cross B was the direction of propagation. And so E has to be either into the board or out of the board. If it was out of the board, you would have E this way, B out. That would give you the correct K. So in this region, B must be out of the board. Okay, well that means down here it'll be the same thing. You'll have E2 and B coming out of the board. And up here, we take E1 to be that way. Then we need B out of the board so that the propagation will be in that direction. So B2 will be directed out of the board. Okay? Now, for the B's and the E's, we have some direction. Now, we're going to use our notation of taking the real part of a complex number to get the electric field. That'll just make the arithmetic easier. E0, E to the I, K dot R, minus omega t, and B the same way. B0, real part of B0, E to the I, K dot R, minus omega t. All right, now, there will be some boundary conditions at the interface. We happen to know what they are. It doesn't make any difference, as we're going to see for the first part of this. But we know there are boundary conditions. You know, the tangential component of E was continuous, and the normal component of D was discontinuous, and so on. But the point is, there are some boundary conditions. Now, that means, regardless of what they are, they will involve these factors. The e to the minus, whatever the condition is, it'll be some condition on the components of that. This will multiply everything. And if we're going to have any boundary conditions, then this thing for each of those three waves must be the same. If that weren't true, then if it worked for one value of t, for example, it wouldn't work for another. Because that would mean the function of t would be different for wave 0 as opposed wave 1 or as opposed wave 2. And similarly, k dot r must be the same for each of the three waves. Make sense to everybody? Well, it's just, I'm going to have some conditions. Suppose, for example, it was E tangential is continuous. That's one of them. It wouldn't make any difference. E tangential is continuous. The vector part of this is contained in that. That's just a number multiplying it. Well, if I arrange it nicely so that this condition is satisfied for one value of t, for all three waves, then the only way it'll be true for another value of t is if the time dependence is the same for each one. Well, that means that that has to be the same for all three. Right? So that means that omega 0 must equal omega 1 must equal omega 2. Right? Now, we know we had a relationship when we derived the wave equation that omega was equal to v times k. Or it's also equal to 2 pi times the frequency. All right? So this answers the question that should have been bothering us all along, and that is we know that when a wave, any wave, obeys the relationship that the velocity is the frequency times the wavelength. So, if the velocity changes when the wave goes into another material, because the index of refraction is different, because the mu's and the epsilons are different, then either the frequency or the wavelength or both has to change. Because the velocity is frequency times wavelength, the velocity changed. So one or the other or both had to change. We didn't know which it was. Now we know. The frequency must be the same everywhere. Now that has a profound significance a little later on. In quantum mechanics, we discover that the energy associated with a wave is Planck's constant times the frequency. And one of the fundamental ideas of quantum mechanics is that photons are indivisible. A photon is either there or it isn't. You can't split a photon into half a photon. And that means when a wave enters this material, either it goes through unchanged, the frequency doesn't change, the energy of the photon doesn't change, or it gets absorbed. Okay, so that's the first observation we make, is that when a wave strikes an interface, the frequency doesn't change, the wavelength does. Okay? Now, the second condition we have to have is that K1 dot R, this is the K dot R part, must be the same as K0 dot R, must be the same as K2 dot R, must be the same as K1 dot R. Okay? But now, this condition is going to be valid on the interface. And so the R is going to lie in the plane of the interface, because the boundary condition occurs at this. So R lies in this plane. So R is along here, for example. So what is K dot R? Well, K dot R is the component of R on this. Okay, well, the component of R on that is going to be K times the sine of that angle. Okay with everybody? So, what we're going to get is K0 sine theta 0 is going to equal K1 sine theta 1 is going to equal K2 sine theta 2. But K is equal to omega over V. And V is C over N. So this means that omega C over N1, where N1 is the index of refraction in the upper piece, must equal omega times the sine of theta 0, must equal omega C, but K1 is also in the upper piece, so it has the same N, sine theta 1, must equal I had K here, C over V, V was C over N. So it's omega N, so the N is upstairs, not downstairs. N1 must equal N2 omega C sine theta 2. Okay? Now, these two tell you that since omega C is the same everywhere, of course, These two tell you that sine theta 0 equals sine theta 1. Or in other words, that theta 0 equals theta 1. The angle of reflection equals the angle of incidence. Now the second one tells you that n1 sine theta 0 is n2 sine theta 2. n1 sine theta 0 is n2 sine theta 2. And those two laws are the laws that govern reflection and refraction. The second one is called Snell's law. It would apply for any wave. It doesn't matter what the boundary conditions are. The mere fact that there are any requires this to be true. Well, it comes as no surprise. Snell's law was known back in the 1700s, although E&M wasn't developed until the latter part of the 1800s. Okay so far? All right, now we tackle what happens when you have a specific wave, like an electromagnetic wave. Now it will depend on exactly what the boundary conditions are. So far, just being a wave is all that mattered. Now we're going to look at specific wave electromagnetic. And for that, we need to know what the boundary conditions actually are. Well, we've worked them out previously from our basic equations. Divergence of D was equal to rho. The curl of B was equal minus the partial of B with respect to T. The divergence of B was equal to 0, and the curl of H was equal to J plus the partial of D with respect to T. Okay? Now, in our case, those are the general ones. And to get the boundary conditions from those, what we did is to consider an interface. This is 1, this is 2. And we have for D, for example, we have D2, we have D1. We drew ourselves a little tiny box, Gaussian box here, and we calculated this. We knew that the integral of divergence of D over the volume was the same as the surface integral, E dot dA over the bounding surface. And the integral over the volume of that would be the charge inside the little box. Okay. Now, the integral over the surface, on this side, D1 and A point in the same direction. So you have D1 times A, only we need the normal component, D1 normal times A. Here, they're going in instead of out. So minus D2 normal times A equals the charge that's inside this box, Q. Divide by the A's and you get D1 normal minus D2 normal. Charge divided by area is the charge density on the surface. So the first boundary condition is that D1 normal minus D2 normal, top surface minus bottom surface, normal components must be equal to the charge density on the surface. Okay? Applying the same thing here, since the rho is 0 over here, it means that B1 normal minus B2 normal must equal 0. So B1 normal is continuous. Now this one. Here, get our two interfaces. And now we've got E. This is 1. This is 2. You got E coming like that. You got E going like that. And now we're going to apply Stokes' theorem. So we have the integral of the curl of E dot dA, which is equal to the line integral of E dot dL around the box, should be equal to minus the integral of the B dt dot dA. Okay? Now, this going around the box, keeping it to our left, will be going this way, E2 times that length, L. 0 here because it's vanishingly small distance. Opposite here, minus E1 times L. But I need the tangential component here because I need that one. So E2 tangential, E1 tangential times L equals, now this, as that goes to 0, this area goes to 0, so that becomes 0. And the conclusion is E1 tangential equals E2 tangential, and the tangential component of E is continuous. And the final one is the curl of H. Okay, well, we can see what will happen there. This just gets replaced by H's instead of E's, and so you get H2 tangential times L minus H1 tangential times L. But now, the dd dt part will be 0, but the J dot dA part J dot dA. But divide this by L, and this was current per area. That makes it current. Divide by L makes it current per length along the wire. So H2 tangential minus H1 tangential is equal K, where K is current per length. In other words, on this sheet, you got current coming out like this. It's the number of amps per meter along the sheet. Okay, so those are the four boundary conditions for electricity and magnetism. Now, in our problem, there's no charge density on the surface, and there's no current on the surface. So for us, we have to have each of these things continuous. D normal is continuous, B normal is continuous, E tangential is continuous, and H tangential is continuous. Okay with everybody? Okay. So this is going to give us four equations. And so let's just start at the top. D tangential D normal continuous. D normal continuous. So what is D normal? Well, you look at our picture up there, and normal means perpendicular to the plane. And so the component perpendicular to the plane is, so let's sketch it out here. So here comes our wave, and we had an E this way. So we have a D in this direction. The normal component is this one. That's normal. Okay. Now, when this goes to 0, that goes to 0. So this angle is the same as that one. And that means I need the cosine of the angle theta 0. And D is kappa epsilon 0 E. So we have kappa 1 epsilon 0 E0 cosine theta 0 for this piece. Okay, now the other side, we have E like that, and so it points in the same direction, upward. So we have kappa 1, because the kappa is the same, E1 cos theta 0, because we've decided this angle was the same as that angle. And now down here, we have this. Well, that's exactly the same thing, except it's kappa 2 epsilon 0 E2 cos theta 2. So this is the first equation. That makes the normal component of D continuous. Everybody okay so far? All right. So now let's make the tangential component continuous. Now here the tangential component I wanted the normal components. I needed the sine, not the cosine. Sorry. Sine. Sine. Now, the tangential components are cosine. And so we have E1 cosine theta 0. Now, this one points in the opposite direction. And so it will be minus, this is E0, minus E1 cosine theta 0 equals, this one points in our positive direction, E2 cosine theta 2. So that is our second condition. Okay. Now we need B normal continuous. Now, in each of those situations, B was out of the board. Since it's out of the board, there is no normal component. It's running perpendicular to the board and therefore parallel to the face. So this just gives us 0 equals 0. Nothing for that one. And finally, we have H tangential continuous. Okay? Now, B is out of the board, and therefore H, which is B over mu, is also directed out of the board, and it's the entire H, because it's all lying parallel to the plane of the board. And so that means that H0, which is, remember, B was mu times H. And so H is B0 over mu1 plus B1 over mu1 equals B2 over mu2. Okay? So those are the four equations that are going to govern the E's and the B's. Yes?
On that B naught
It's mu1 so far. Now I'm going to make them all mu0. Most materials have mu essentially equal to mu0, unless they're ferromagnetic.
But it is supposed to be.
It is mu1 because that was the conditions we made. Mu1 epsilon 1 in the top, mu2 epsilon 2 in the bottom. So that's the story in general. Now, to make the arithmetic a little bit simpler, we're going to use the fact, we're going to assume that mu1 is equal to mu2 is equal to mu0. It's not necessary to do that, it just makes the algebra a little simpler, and it's almost always the case. So, we then have three equations to deal with. And this one, we're now going to write everything in terms of e's. Now, we know that B was equal to E divided by the velocity, which was E divided by C over N. Okay, so this becomes E0. We're going to replace, I'm going to multiply out the mu's because I'm making that assumption. And so we have E0 N1 divided by C plus E1 N1 divided by C is equal to E2 N2 divided by C. So I'm going to cancel out the C's. And now I have just that. Now, go up and look at the top equation. Divide out the epsilon zeros. And I've got, well, we know that N is equal to C over V. And V, well, we wrote this out over here. I don't need to do it again. We've got N written up here someplace. The mu zeros cancel, and you just get epsilon over epsilon 0. Okay? So, this first one, what is epsilon over epsilon 0? And it was the square root from what we have up there. And so it is kappa to the 1/2. Right? So this makes it, that top equation, kappa then is n squared. So I have n1 squared epsilon 0 E0 sine theta 0 plus n1 squared epsilon 0 epsilon 1 sine theta 0 equals n2 squared epsilon 0 E2 sine theta 2. Now, I can cancel out the epsilon zeros. N1 sine theta 0, N1 sine theta 0, N2 sine theta 0. But N sine theta 0 is equal to N2 sine theta 2. Snell's law. And so I can cancel one of the n's and the sines, leaving me with N1 E0 plus N1 E1 is N2 E2, which is exactly the same as this. So what I end up with then is two equations. N1 times E0 plus E1 equals N2 E2. That is this equation and the top one. And E0 minus E1 times the cosine of theta 0 is equal to E2 times the cosine of theta 2. And so those are the two equations I need to solve. Because I had Snell's law. N1 sine theta 1 is N2 sine theta 2.
I recall you saying that, I just don't.
Okay, up here, Snell's law on the left upper box there, N1 sine theta 0 is N2 sine theta 2. So I canceled out an N1 sine theta 0 across the board. N2 sine theta 2 is the same as N1 sine theta 0. So I can cancel out an N1 and a sine theta 0 and an N2 sine theta 2. All right, so all I got to do is solve these two equations. And so what I do is I take this one and I solve for E1. I'll just solve for E2 here, that's easier. E2 is N1 over N2 times E0 plus E1. Now put that down here. E0 minus E1 cos theta 0 is equal to N1 over N2 E0 plus E1 cos theta 2. So we'll get the E1s together, and we get E1 times N1 over N2 cos theta 2 equals E0 cos theta 0 minus N1 over N2 cos theta 2. And so I get what I'm really interested in, E1 over E0. The ratio of the reflected electric field to the incident electric field is cos theta 0 minus N1 over N2 cos theta 2 divided by I missed a, obviously I lost a term here. E1, I had this. And I had that. I brought this one over here. So this has an additional plus cos theta 0. Okay, so when I'm solving for this, I got that in the denominator now. N1 over N2 cos theta 2 plus cos theta 0. Okay. So that's E1 over E0. Now we can get E2 over E0 from the statement up there. Divide both sides by E0, and you get N1 over N2 plus E1 over E0 plus E1 over E0 cos theta 0 minus N1 over N2 cos theta 2 divided by N1 over N2 cos theta 2 plus cos theta 0. All right, so putting them over a common denominator here, we'll have cos theta 2 times, we'll have N1 over N2 squared. That's that one. Minus N1 over N2. And then you'll have cos theta 0 times N1 over N2 plus 1 divided by N1 over N2 cos theta 2 plus cos theta 0. So now we have found the electric field in the reflected wave and in the transmitted wave. Now, can you think of any way to check and see that we haven't screwed up the algebra? Do you know a limit for these? Think of a condition where we know what the answer should be. Suppose N1 were equal to N2. What would happen? It'd go straight through. So when N1 is equal to N2, we ought to get E1 over E0 is 0 and E2 over E0 is 1. So let's see if that happens. Well, if N1 is equal to N2, then the angles are all the same. And so this gives you cos minus cos gives you 0. So that works. What about this one? Well, this is 1 minus 1, so that's 0. This one is 2. And down here, that's 1, that's 2, so you get 1. So the limits are right. So things are looking promising. Okay? But now what we're really interested in is the intensity, the fraction of the incident intensity that goes through. So what was the intensity? Well, we did that on Friday, and it was given by our Poynting vector S, which was E cross H. Right? So we should calculate E cross H incident, E cross H reflected, and E cross H transmitted. Making sense? So let's see what these things are. Everybody followed this all right? Okay. So I'll write this up for you and pass it out as notes on Wednesday. So S is E cross H, which is E cross B over mu 0, because we're taking mu to be mu 0. But B is E now what is B? Well, if this is E, this is B, then K comes out of the board. And so B would be given by K cross E. S is Poynting's vector. That was the intensity, the energy per second per area. carried by the wave. That's the thing we derived last time. So this is E cross K cross E. Or we know that the magnitude, that this is then just it's got a direction K hat. And you remember our relation was omega equals dk. So K was omega over V. So here we have K hat cross E. And we knew that the magnitude of B was just 1 over the velocity times E. And so 1 over the velocity times E. So we need 1 over the velocity here. And 1 over the velocity is N over C. So that's S. So let's just work out that triple product. E cross K cross E. It's this dot that times K, E squared K hat, minus this dot that times that, but K dot E is 0. So you simply get E squared K. So S then is equal to E squared N divided by C times K. Okay with everybody? Yeah. The vector identity is the triple product rule. A cross B cross C is C dot A times B minus B dot A times C. Okay. Now, what is the energy incident on the plane? Is it S? No. It's S dot N. Because you've got the plane sitting like this and S coming like that. The energy striking the plane per second is this component of S. And so to get that, I have to take the dot product of S with the normal to the surface. In other words, I need the component of S, which is normal to the surface, which multiplies those things by cosines of theta. So, intensity coming in is E0 squared N1 divided by C times the cosine of theta 0. The intensity reflected is E1 squared N1 over C cos theta 0. And the intensity refracted going into the material is E2 squared N2 over C cos theta 2. So, the fraction of energy reflected is E1, I1 over I0. And you simply get E1 squared over E0 squared. The fraction transmitted is a little different. It is E2 over E0 squared. But then your C's will cancel out. You'll have N2 over N1 cos theta 2 over cos theta 0. What should I1 over I0 plus I2 over I0 be? Well, the energy had to go somewhere. So the energy coming in plus the energy equal the energy reflected plus the energy transmitted. So if we haven't screwed up, it had better work out that E1 squared over E0 squared should be equal to this other thing on the right-hand side. So that's a check we should make to be sure we haven't screwed up the arithmetic. Okay, now, there are two possibilities. I've looked at one of them. I took E that way and B then parallel to the plane of incidence. But I could have had E parallel to the plane of incidence and B the other way. So there are two different sets to consider. E parallel to the plane of incidence and E perpendicular to the plane of incidence. And I've done the case E perpendicular to the plane of incidence. So we need to go back, and I'm not going to do it. I'll leave that for an exam question or something like that. We need to go back and calculate the other orientation. Now, that turns out to be important because any ray of light coming in can be split into components in those two directions. That's the reason Polaroid sunglasses work. It'll turn out that the reflection, the amount reflected, is very different for those two cases. And in one of the cases, with the proper choice of angle coming in, nothing will be reflected, called Brewster's angle. And that's the reason Polaroid sunglasses work. Okay, have a great day, and I'll see you all on Wednesday.